Yeah, so I'm going to talk about a number of Kubernetes related things that we're doing at UChicago. We have found that, Kubernetes is a really powerful, albeit complex, framework for sort of bridging our traditional infrastructure that we've provided to users with more forward-looking tools and platforms that I think will come to be something expected by users in the future. We've been using Kubernetes for, gosh, like over 4 years now. I think we started using it halfway through 2017. I think that comes out to a little over 4 years. And in that time, it's become foundational for many of our projects. And so I will try to touch on as many of these as I can before you guys shove me off the stage. Yeah, so we have a lot of stuff here, and I'll just go right into it. So one of those projects is this Scalable Systems Laboratory. This is a moderately sized Kubernetes cluster, on the order of, I guess, 75 machines, older machines that we have split into a couple different clusters for the purpose of providing an area for folks working in the IRIS-HEP project to develop and test and scale and productionize various kinds of software that they're building that's relevant in the sort of HEP computing space. And so we set these clusters up and we gave people accounts on them, and they went out and they built all sorts of really cool stuff. A lot of stuff for data transformation. People have built things for analytics. People have been doing things like machine learning, caching, functions as a service, all sorts of really interesting stuff with Kubernetes. And so we've taken a lot of what we learned from building this Scalable Systems Laboratory, and we used it as a basis for a new kind of platform for users that we just call our analysis facility. As I kind of alluded to before, there's a lot of interesting new technologies, new frameworks and such that are being developed. And a lot of those frameworks have used Kubernetes as sort of their cornerstone technology to get all the scaling and load balancing and interesting, nice features that Kubernetes gives. So what we have done is built a Kubernetes based infrastructure that's flexible enough to support sort of our traditional batch users who really just want to SSH in and Condor submit some jobs, and that's really where they live, and they're happy with that. But something that's also flexible enough to be able to support some of these interesting new frameworks and things like that, and to think about how we slide resources back and forth between those two different use cases. So one example of one of these frameworks that we're using on our analysis facility is this tool, ServiceX. And the idea behind ServiceX is that it can filter and deliver data in columnar formats. So for example, it can take the Atlas XAOD format and transmute it such that it can be delivered to a end user analysis as PyArrow, awkward arrays, or it can do flat root files or whatever. And this can be used with other tools like Coffee Casa and Coffee. And it sets up users such that they can do work in what folks are kind of calling like Pythonic analysis, where you have these tools that work really well with Python, and you do everything inside of a Jupyter notebook. And all of that stuff. And so that's the kind of thing that we want to support on our analysis facility. And so at UChicago, we were charged to build one of these analysis facilities for Atlas at the scale of about 1,000 logical cores and about a petabyte of storage. So we went out and got 16 of what we call hyperconverged nodes. These are machines with just a lot of memory, a lot of disk, a lot of CPU, and we just sort of hand those off to Kubernetes and let it manage all of those resources. And those machines are both serving a Ceph object store, as well as Condor and things like that that users use to do their analysis. We also have what we call login nodes, which are sort of just traditional batch SSH logins that also have some capability to host Jupyter notebooks for users. We additionally received another 16 nodes that are sort of fast local disk machines. So they're full of NVMEs and for sort of fast data access. Yeah, and so this is kind of just a cartoon of how this works. Users can come in. They can come in either through a SSH or they can come in through a Jupyter-based portal. They can, if they want to run workloads, those are farmed out to the Kubernetes cluster, which is running containers that have Condor in them. If they have some other, workload management type of thing that they want to bring in, they can do that. And then for our users that are using Condor, we can take advantage of all the great features there to do flocking, to run jobs on our tier 2 center that is, literally the next rack over. Or next several sets of racks over. And yeah, there's this nice user portal where people can come in and they can sign up. They can use their CERN credential or their institutional identity. And those go through an approval process, and then we put them onto the machine. Yeah, so zooming into the Kubernetes pieces, just a little cartoon here of how this works. As a user, you have a number of different ways to use the platform. Again, you can either use one of these SSH hosts and you just talk to Condor as usual, and all the Kubernetes stuff is sort of totally abstracted away from you. Alternatively, you can go through the web portal and you can ask for a Jupyter notebook, in which case you're provisioned a notebook on some machine in the cluster, and you can do all sorts of fun stuff there. There's some GPUs attached, so you can do machine learning and all that sort of thing. And then the real power users can come in, of course, and they can say, I have this fancy distributed complex application that I want to run directly in Kubernetes, and we can enable them to do that and give them access to that sort of thing. One of the things that we have found through hard-won experience is that running a Kubernetes cluster without some kind of tool to manage all of the various objects in Kubernetes is kind of like running a cluster without having Puppet or Ansible or one of those configuration management tools. So sort of the moral equivalent is this GitOps style of application deployment in Kubernetes. So using FluxCD, there's a number of options out there, but we chose to use Flux. We have all of our configuration living on GitHub. And so any kind of new application or extension to Kubernetes that we want to put on our cluster all lives in this Flux repository. And so we have all the Kubernetes stuff like the ingresses and load balancers and all the monitoring and certificate management and all that stuff is in Flux, as well as our Ceph deployment and Condor and all of that stuff. That all lives here. And this has made life so much easier, instead of checking the cluster one day and seeing that there's test 1 through test 9 and they've been running for 62 days and you have no idea what image it is or anything like that. This is main thing so we can sleep at night a little bit better. For our Condor setup specifically, we've done something a little unusual, I guess. We've chosen to put our SCED on a separate host from the login nodes. We would really like it to be where users can log into any one of the login nodes and they can submit and see sort of a single unified queue. You can be in a login node, you can be in a notebook, it doesn't really matter. You see this single queue. All the daemon authentication in Condor is fully tokenized. And so the way we make this work for users then is that every user has this .condor directory that holds a token that allows that job submission to the remote SCED, and then all of the nodes have a shared home file system. So users, can access their files from anywhere in the cluster. And then all of the execute nodes are all just pods in Kubernetes. And we've taken sort of this conservative piecemeal approach to moving those daemons inside of Kubernetes. If you have any experience with Kubernetes at all, you're probably very familiar with how fickle its networking can be. And so we haven't moved all the daemons there, but that's something that we could potentially do in the future and just have the entire setup inside of Kubernetes. So for our execute nodes, our pods are configured to have 80 logical cores per worker. So we give the lion's share of our resources to Condor. And then we have these various file systems. There's a fast SSD, I guess NVMe-backed home file system for users. There's this Ceph-based data volume. There's CVMFS. All of that gets automatically mounted into the containers. And then the Condor pods are dynamically configured based on values from the Kubernetes downward API. So you can just say to Kubernetes, I request 384 gigabytes of memory or whatever. That gets transformed by this downward API stuff into, you tell it that it requests memory. You want to define this environment variable for Condor memory as request memory with the divisor of megabytes to convert it to megabytes. And indeed, when you have your container running, you see that it has about 384 gigabytes of memory. My exercise to the reader then is to do the same thing for CPU, which is a little challenging because Kubernetes can schedule CPUs in terms of milli-CPUs, so sub-CPU allocation. For the Ceph file system, we have a 1 petabyte usable shared file system, which we call $data for users of the analysis facility. It has something like 230-ish hard drives. They are configured for 3x replication. I won't go too deeply into the details about the Rook configuration, but we have run Ceph for many years, and what we really want to focus on is performance, because users really know how to trash a distributed file system, just given a limited budget and inability to take a dump truck full of money to IBM, we really wanted to focus on performance with our Ceph cluster. Ceph also has a lot of really nice features now for like setting QoS and visualization and all this stuff. So they have this really cool Ceph Dashboard. I have found this is super useful. You can see the IOPS and the throughput for all your clients and all that stuff. You can apply now QoS limits such that, at least for certain aspects of Ceph, like block devices, for example, you can limit the number of IOPS that a given block device uses. So we found this recently where we had a lot of monitoring VMs, and they were, collecting and crunching on all sorts of monitoring data, and then they were eating up all of the raw IOPS capacity for the cluster. And so you can apply this really nice QoS to trim that back a little bit. So another thing, so moving beyond the analysis facility, another thing that we have been working on for several years now is this idea of doing federated operations, where we have sort of Kubernetes-based clusters sprinkled around, and we federate them together in such a way that users of this platform can build applications and push them out to all these centers and rapidly iterate and do all this really cool stuff, with the goal that overall we can try to reduce operational costs by sort of moving a lot of the responsibility for applications to the people who are writing those applications, sort of like a DevOps kind of model. And the culmination of that work is SLATE, which stands for Services Layer at the Edge, and it implements a lot of this work that we've done. And we also did a lot of investing into developing a trust model for how this works, how you actually can go to an institution and say, I want to run a service on your network, and within your institutional boundaries, and what does the trust look like for that. From a packaging perspective, we've done a lot of work in taking commonly used applications in our community and packaging them up such that they can be deployed via SLATE. But if you don't want to join the SLATE Federation, you can also just add this catalog of applications to your own Helm configuration, and you can Helm install a Frontier Squid or XCache or other interesting things like Perf Center test points and OSG hosted CEs, things like that. Yeah, we had this really great engagement with the TrustedCI folks, and they taught us a lot about how to think about security policies and what that means and how to put together some of these things. And so we've built out a lot of documentation and policies and things like that for how one might go about implementing this this federated model and how it is implemented in SLATE. Within US Atlas, we have had an ongoing project to use SLATE to do some federated service deployment. So every tier 2 in the US, in US Atlas, has a baby Kubernetes cluster, and it has joined the SLATE Federation. Each of those tier 2s are sort of responsible at the level of keeping that hardware running and keeping the operating system up to date and all that sort of thing. For the applications, we have introduced a federated operations team who will actually go and deploy and manage those applications onto the clusters. And so the 2 applications that we're doing right now are Squid and XCache. And so this is configured to use something that we call SLATE flavored GitOps, which is similar to Flux, but instead of managing things at a deployment level, Kubernetes object level, it's really managing things at the level of, here are all of your SLATE clusters. You put these in a GitHub repo. You put the configuration parameters for them there and all of that stuff. And so when a user or an operator comes in and updates one of those applications, it will actually go behind the scenes, do the actual update, send an email, let everybody know that something has changed. And so, we have introduced a lot of really nice transparency to the operations for these kind of services. And then the SLATE team, of course, will keep those Helm charts and Docker containers and all of that stuff up to date. So when there are things like a vulnerability in some application that we have deployed across this federation, somebody can go through and make sure that we do the SLATE instance restart or whatever it is, and make sure all those things are up to date. And so it's kind of interesting to know, we can know exactly what version of Squid or XCache or whatever is running on every tier 2 site. And yeah, this is just another cartoon about how this could work, or how this does work. Traditionally our sites have, they've done the full stack. They've managed hardware and the operating system. They've installed all the services. They've learned all the weird corners of all of the WLCG software and other software that they have to run to keep their site running. And in this new model, in this FedOps model, what we propose is that sites really should, they manage their hardware, they manage the operating system, they manage sort of this service endpoint, and somebody else can manage the services. And so this kind of becomes more like how sites provide CPU or provide storage to the collaboration. Yeah, so XCache, you've heard a lot about the OSDF. Within Atlas, I guess we have like an Atlas data federation, for lack of a better term. So we have an XRD-based caching infrastructure in Atlas, and many of these Atlas sites, as I was just saying, have these caches deployed there, and so they're used for various purposes within Atlas. And so we have all of this in this GitOps repository where all these configurations are kept. We have all the tier 2s in the US, plus some other tier 2s in Europe and elsewhere. Likewise with Squid, same thing. We have Squid deployed. It's caching namely frontier data and CFS, and that's all managed in this GitOps fashion, just like XCache. For PATh, we have been taking advantage of this river cluster, the Scalable Systems Laboratory cluster, to provide some redundancy for various PATh services. And what I like to call soft load balancing in the sense that there's a human in the pipeline who chooses where things run. And so for PATh, many of these hosted compute entry points are running at UChicago on the SSL cluster. And so you see your name in lights here. Another thing that we're doing is we're working on redundancy for this container registry service that we're working on with the PATh folks. And the idea is that you'll have this container registry, and you can grab stuff from the CHTC site, or you can grab it from the UChicago site, and all this has nice redundancy built in, failover, that sort of thing. Another one of the things we're working on is with Fab, which is the Fabric Across Borders. Fabric is a project to put programmable platforms inside of the network. And so what we have done is we're working on this demonstrator where we have this ServiceX tool that I mentioned at the beginning of the talk that does all this sort of slimming and filtering of data. And so we want to put that service in the network sort of next to the data origin at CERN, do all of that filtering, and then send the smaller final product across the transatlantic link to our analysis facility at UChicago, where users can then work on those more refined data products. Yeah, and so this is some collection of screenshots showing this. So we have this Fabric node. It's a Fabric Kubernetes cluster registered in SLATE. So they have like I think it's an OpenStack API, and then we've layered a Kubernetes cluster on top of that, and then we've registered that Kubernetes cluster in SLATE. And then the end user has this notebook that they can, I think on the next slide, they can get input files from CERN, and they can shovel those into ServiceX, and they can get these columnar formatted data out at the end, and they can use that for analysis and make some nice plots and all that stuff. So we're finally to the end of the talk. So yeah, we have been doing a lot of work with Kubernetes for the past few years now, both within our site and also in this distributed fashion for facilities and collaboration. So we've built this Kubernetes-based testing and R&D platform with the Scalable Systems Laboratory for IRIS-HEP. With PATh, we are operating services like these compute entry points and things for container registries, things like that. In Atlas, we have built a Kubernetes-based analysis facility that allows both that traditional batch access and also these sort of forward-looking technologies being developed in IRIS-HEP. And with SLATE, last but not least, we've been working on developing this trusted federated operations model for deploying, operating, and maintaining services. Yeah, so that's all I have. Thank you very much.